I will start in a couple of minutes. Right, so I'll share my slides. Okay, so this is the 11th live session of this course. And as always, I'll be first discussing a summary of the week 11 videos, and then we'll solve the assignment 10. So in the previous class, we had just started looking into folding dynamics of protein. Now we'll look more into more mathematical details of that. So we know that life is marked by something changing over time. So how and why is this change happening? Proteins, which form the fundamentals of all biological structure and function in the body, are dynamic molecules. They keep changing their conformation, and based on that, they are either active or inactive. And these dynamic motions are very essential for their functions. If somehow you manage to capture the protein or trap it in a conformation where it is not able to be dynamic, then it will become non functional. That is why proteins are called soft matter, because they are not rigid, they are dynamic with multi-dimensional energy landscape. So we had seen the energy landscape of the protein before, and why is it called multi-dimensional is because not only, so in the y-axis you can imagine it as energy, so it's of lowest energy will be at the bottom, which is the folded or native structure, which is the most stable, and the higher energy states will be along the top. And on the x-axis, you can imagine it as entropy. So at the top of this folding funnel, energy is also high and entropy is also high. Entropy high means that the protein is very dynamic. The randomness is very large and it is sampling a large number of states. That is why we are calling it as um, a dynamic structure. And since it does not have, it is not restricted to a particular state, it also has a large amount of energy. So this is the folding funnel, and as you go down the folding funnel, both the entropy is decreasing and the energy is decreasing. So slowly the number of degrees of freedom are decreasing as more and more intramolecular interactions form, and these lead to stabilization of the molecule, which is why the energy is also decreasing. Now, the relative probabilities, while studying this energy funnel, you can find out that what is the relative probability that the protein will occupy, say, this intermediate state compared to the native state. And this will give you an idea of the thermodynamics, that is the energy difference or the entropy difference. Another thing is the kinetics, which is the energy barrier required. So imagine the protein is in the native state. How much energy will it need to cross over into another intermediate state? That is determined by the kinetics. Just give me 1 second. So why we saw in the previous class also that we are calling it multidimensional. So what is the fourth dimension? You have three dimensions, the x, y, and z axis, because the protein is a three-dimensional structure. The fourth dimension is your time. That is, according to time, how is the structure changing? So basically, you have the structure of the protein, which is changing with the dynamics, and also the protein is in different stages of folding as it goes down the folding funnel. And the function of the protein is very much dependent on the structure. So basically, the folding and dynamics together with the structure, all three of these talk about the function of the protein. Because if the protein is not dynamic, it will not be able to carry out its function properly. And also, if the folding is not happening, it will not be able to obtain the structure which is required for the function. So all these three are essential for the function of the protein. Then you have something called the energy landscape, which is the same as the folding funnel we saw in the previous slide. So you have various intermediate states in the upper levels of the energy funnel, and these intermediate states can be of various different structures. But as you go down the folding funnel, there is only one native state, which is the most stable state of the protein with the lowest energy, which is shown here as N. Now, NMR can tell us about how the conformation can change when going from the native state to the different intermediate states during the folding process or during the dynamic movement of the protein. An example is given here. This is deoxyhemoglobin, where it is not bound to oxygen, and on the right is oxyhemoglobin, where it is bound to oxygen. Between these two structures, you can see if you consider an axis along the z-axis, here the axis shifts by around 15 degrees. So this change in structure is happening due to the binding of oxygen, and the protein is able to change the structure because of the dynamic nature of the protein molecule. So if somehow the structure was fixed in deoxyhemoglobin conformation, then it would not have been able to change its shape, and so it would not have been able to bind the oxygen. So the very function of the protein would have been lost if it lost its dynamics. Now, there was a paper that is mentioned here which studied the dynamics of aromatic amino acid residues in the globular conformation of a protein called BPTI, the basic pancreatic trypsin inhibitor. So you have aromatic amino acids, like phenylalanine or tryptophan or tyrosine. Now, how is the aromatic amino acid conformation changing with time? We can imagine two possible conformations where suppose you have a residue here shown by blue, and the orthocarbon is shown as red. So if it is in this conformation where the residue blue is away from the red, that will have greater distance, or if the blue is turning and coming towards the red, it will have shorter distance. So depending on this, the NOE will be different, and that will give you an idea about which conformation the aromatic amino acid is adopting. Now, a temperature dependent study was done on the aromatic amino acids within the hydrophobic core of the protein. So aromatic amino acids, we know normally these are buried within the hydrophobic core because the aromatic residue is hydrophobic, so it does not want to be exposed to the solvent. The BPTI protein shown here has many aromatic residues, so you can use it as a probe for the whole protein. Now, at low temperature, you have a certain peak for these aromatic residues, and as the temperature increases, some of the peaks are shifting. So if you see this large peak, it is appearing somewhere here, but here it is shifting towards this side with increased temperature. Similarly, some peaks, the intensity is decreasing due to broadening. So you can see peaks are very sharp here, but here they have kind of merged into one broad peak. So basically, why this happens is because as you increase the temperature, the dynamics increase. That is, the motions that are happening for the aromatic residue, they become faster and faster. So you're no longer able to distinguish two conformations. So suppose you have one peak for this conformation and one peak for this conformation. As the temperature increases, both these peaks will merge into one broad peak. So that is kind of what is happening here. So this also gives you an idea about the dynamics of the protein. So now there are several processes occurring in proteins which have different time scales. And so in order to study these processes, there are different NMR methods. Just one second. Right. So as I was saying, there are several processes occurring in proteins, and each of these processes have different time scales. So you can have local dynamics happening, which consist of vibration within the bond, or maybe there is a methyl group that is rotating, or a loop that is moving, or just the side chain of the amino acid rotating. So these are all part of local motions, and they occur on faster time scales like nanosecond, picosecond, and femtosecond. Or you can have collective motions. So you can see this is a protein shown here consisting of two domains. You have one domain here and one domain here. So suppose these two are coming closer or moving away from each other. So the domain as a whole is moving, and that is called the collective motion. And these have longer time scales from microsecond, millisecond to second. So normally the NMR relaxation processes that we'll study cover all possible time scales from second to picosecond. So most of the motions can be detected by the NMR process. Only the femtosecond bond vibrational methods, you might need some other processes like IR or so. So we won't look much into that. Otherwise, another advantage of NMR is that it can give you information, because NMR can give information on such a wide range of time scales. So it is very useful in studying different motions. So again, there are several methods other than NMR which can be used to study a molecule at atomic resolution. These can include X-rays, but the problem with X-ray is that you need a crystal. So you're trapping the protein in a particular state. You are not allowing the protein to be dynamic or to move around in different conformations. NMR you can use, that's a good technique, but the disadvantage of NMR is that it is not very good for very large molecules. Then the lines merge and broaden so much, it is not able to be resolved. Then there is cryo-electronic microscopy, which is good for bigger molecules, but it is still an emerging technology, and the setup is not there in many places. Then you have SAXS, or small angle X-ray scattering. The problem is that it's not very much resolved technique. It will give you the qualitative details, but not at atomic resolution. You can also have free electron laser, but it's a very invasive technique, meaning that it's a high power laser is used on the sample, so the sample itself gets destroyed. So all of these techniques have some advantages and some disadvantages. So often two or more of these techniques can be combined depending on what you want to study. So since this is an NMR course, we will look at how NMR is used to probe the protein dynamics. Basically, the nuclear spin relaxation measurement provides different informations. So there are fast motions on the time scale of picosecond to nanosecond. So you can see the very fast motions here, which are the backbone dynamics or the side chain rotation. So suppose you have a phenylalanine side chain here, and it is just rotating like this. That is a picosecond to nanosecond motion. or you have a backbone forming a helix and a kind of loop, and the helix is unwinding or it is turning into beta sheet. So the backbone conformation is changing. These are very fast scale motions from picosecond to nanosecond, and these can be studied in the laboratory frame of reference itself using nuclear spin relaxation. Then you have motions that are slightly slower, from microsecond to millisecond time scale. These can include, like, suppose you have an open loop and the loop is turning to form a hairpin. So suppose you have an open loop here and it is turning to form a closed loop like this. So because it involves a large section of the protein, it is a comparatively slower motion from microsecond to millisecond time scale. Or you can have secondary structure formation. So from a random coil like this, it is forming secondary structures like alpha helix or beta sheet. That is a millisecond to nanosecond time scale. So these are intermediate time scales, and for that you need the rotating frame of reference. And finally, there are very slow motions, which are basically protein folding. So from a completely random coil structure, if it is forming a folded protein, this is a very long time scale motion. It can take anywhere from 1 millisecond to 1 hour. Or suppose there is aggregation of proteins. We studied aggregation in one of the previous classes for the dynein protein, and we saw that it can take up to 1 year. So for these motions, there are special techniques to be studied, which include magnetization exchange spectroscopy or ZZ exchange, which is something we have looked at before. Now we look at this fast timescale motion occurs in the local minima of the energy landscape, that is local motion, while slow timescale motion occurs when the entire protein goes from one state to another, which is called the global motion. So just imagine this is the protein folding funnel, and you can see there are small variations within one. So imagine this is state 1 and this is state 2. So within, you can see this is state A shown here, this is state B. So within one state, you can have certain changes in conformation due to local motion, and these are very fast timescale motions. You can see nanosecond or picosecond. But if the protein is going from state A to state B, this is a change in the entire conformation of the protein. So it requires a longer time scale from microsecond to millisecond. You can see here protein going from one state to another state. It requires a much longer time scale, and it is dependent on the energy difference between the two states of the protein. So these slower timescale motions ranging from microsecond to millisecond are due to large amplitude collective motion, which basically means large amplitude means that the amount of motion is large. You can see from this state to this state, there is a lot of conformational change between fewer number of states. So that here there are only two states, whereas you can see in the local motion, there are so many local minima. Now, an example of this global motion of the protein is cis-trans isomerism of one of the, you can see one amide bond here is going from cis to trans. So this is a very slow scale motion, again occurring on this microsecond to millisecond time scale. And often this cis-trans isomerism is a rate determining step in enzyme catalysis or signal transduction or protein-protein interaction. So out of cis or trans, one is the functional isomer and one is the non-functional isomer. So this large energy barrier between the two states of the protein has to be overcome so that it can adopt the functional isomer and carry out whatever function the protein is supposed to carry out. And in the local motion, the energy barrier is very low. So just by varying the temperature a little bit, or that is with thermal fluctuations, you can interchange between the states very nicely. But for the global motion, you require a lot longer time. Now, we will look at relaxation, at the different processes of relaxation in this class. So just 1 second. I'll just mute you. There is some background noise, so I'm just muting you. Right. So relaxation is the process by which the spin returns to its equilibrium population distribution. We know that the initial magnetization is in the Z direction. A 90-degree pulse is applied and the Z direction magnetization comes down to the XY plane. Now, slowly, so after the pulse is applied, you allow some time to go, and slowly again, the magnetization in the initial direction, that is the Z direction, is restored. So this process is called the relaxation process, whereas the spin is going back to its original direction, that is in the Z direction. This relaxation is governed by fluctuations of local fields experienced by the nuclear spin. So we saw that the spin is oriented in a particular direction in an external magnetic field, normally the Z direction. Due to application of some pulse or other fluctuation in the local field, the spin is reoriented in the XY plane, and this reorientation can cause variation in different interactions, such as the chemical shift anisotropy CSA or the dipolar coupling DD. We will look into these in the coming slides. And the process by which this reoriented spin is going back to its original position is called relaxation. Normally, for studying relaxation, heteronuclei like 13C or 15N are well suited because 1H has a very complex relaxation mechanism. So, for spin relaxation in proteins, there are two major processes. One is the chemical shift anisotropy CSA, and one is the dipolar interaction or DD. So basically in CSA, what happens? Spins are oriented in different directions, and each direction has a different resonance frequency. So you can see here that due to anisotropy in the chemical field, instead of the spin just been oriented here, there are some spins oriented here, some oriented here, similarly on the other side. So it is not oriented in one particular direction, but due to these fluctuation in the local field, there are spins oriented in different directions in the XY plane. And due to this, each orientation will have a different resonance frequency. So you get multiple peaks close together in the chemical shift. And what you observe is an envelope of all these fields. So instead of observing a sharp peak, you observe a slightly broad peak, which consists of different chemical shifts due to the different orientations. Now, this is called chemical shift anisotropy. And suppose you allow the molecule to tumble a lot. In that case, all these anisotropies will balance out and you will again get the sharp peak, which is normally observed in solution state NMR. So in solution state NMR, you allow the molecule to move a lot in the solution by Brownian motion, and that will average out all these anisotropies and they will cancel out. So you will again get this sharp peak back. The other method of relaxation is called dipolar coupling. So suppose you have two spins shown here as 1 and 2. The distance between them as R12 and the angle from here to the external field B0 is shown as theta. Due to interaction or dipolar coupling between these spins, there is a splitting that occurs and a broadening here. This happens due to dipolar coupling. So this is something we have already seen before, that is dipolar coupling. And this is another way of spin relaxation in proteins. So now in dipolar coupling, there is a certain formula here by which D, that is the dipolar relaxation, is defined as a constant mu0 by 4 pi into h bar, the Planck's constant. Then the gyromagnetic ratio of the two spins 1 and 2 are multiplied, and it is divided by the distance between the two spins cube. And there's also an angular dependence on this theta, which is 3 cos square theta minus 1. So as the distance between the two spins decrease, you can see the denominator will decrease. So overall, the dipolar interaction will increase. So you can just remember this formula, which shows how the orientation of the two spins theta and the distance between the two spins r is affecting the degree of dipolar interaction. And as for chemical shift anisotropy, you can see I was also talking about this earlier, that due to fluctuations in the local magnetic field, the spin can be oriented in different directions. And so there will be a lot of chemical shifts near each other, and you will see a broad envelope. So this happens when you are allowing the spin, you're not allowing the spin to rotate. So if the molecule is, say it is solid state NMR, and you're not allowing the molecule to tumble, so the frequency of rotation is 0, in that case you will observe this kind of multiple lines, that is, you will see a broad envelope. But as you increase the tumbling of the molecule, you can see the new rotation is increasing till at this point where the frequency of rotation is very high, meaning that the molecule is tumbling very fast. So then all the anisotropy will get averaged out, and you will see an isotropic spectrum, that is a single line. So in this way, the chemical shift anisotropy can be cancelled out. Now we will define something called the correlation function. Now imagine that you have a rigid rotor. So imagine that there are two spins, M1 and M2, and they are rotating like this in this direction. You can see the direction shown by the line. So the correlation function defines, so we are studying the protein dynamics. So the correlation function will define how this spins will move in an isotropic diffusion. The correlation function is defined like this: 1/5 of exponential minus t by tau c, where tau c is called the correlation time, which is the time that it takes for the function to completely decay. And we know correlation time is basically the time for tumbling of the molecule. Now we know that if a molecule is big, it will tumble very slowly in solution. So correlation time is also defined as the amount of time the molecule takes to rotate 1 radian. So suppose the molecule is very big, so it will take a lot of time to move even a small distance. So correlation time, you can see here it is 100 nanosecond. And because the correlation time is large, the function will decay very slowly. You can see it is decaying very slowly. And if you have a small molecule, the correlation time will be very short because it will rotate very fast. So you can see correlation time here is 1 nanosecond. And if the correlation time is small, the function will decay very fast. You can see it is decaying like so fast, even around 10 nanosecond. So again, to repeat that, short correlation times will cause the correlation function to decay rapidly, you can see here, and long correlation time will cause the correlation function to decay slowly, which you can see here. The correlation time depends primarily on molecular size and shape, which we just talked about, that big molecules will have large correlation time and small molecules will have small correlation time, and as well as solvent viscosity or temperature and other conditions. So basically, this will define how the dynamics of a big or small molecule occur and how fast that decays with time. Now, we defined a term correlation function. Now we'll define another term which is called as the spectral density function. The spectral density function is the Fourier transform of the correlation function. Just as rapidly relaxing time domain gives rise to broad lines, short correlation times will have a broad spectral density function. So what we saw is that if something is relaxing we saw this in the previous class also. If you remember studying the protein NMR and ligand NMR, we know that the protein has is a rapidly relaxing relaxation time, and so the protein has a very broad line. Similarly, you can correlate the correlation time with the spectral density function. You can remember the formula of the spectral density function. You can see that since the denominator has tau c squared, it will have more effect than the numerator. So short correlation times, that is, if the denominator is smaller, will increase the value of J, that is, it will give a broad spectral density function. You can see here, short correlation times, imagine this 10 nanosecond, the spectral density function plotted in Y is quite broad. When it is even shorter, it is so broad that it appears like a straight line. This makes sense. Molecules that tumble very rapidly can sample a wide range of frequencies. That is why when you have a short correlation function, you can see tau 10 nanosecond short correlation function, you can see how many frequencies are coming under this line. And I'll just discard this. And if you have a long correlation function like 100 nanosecond, you can see that it can only sample a very limited number of frequencies, because then it is becoming zero. And this qualitatively also makes sense, because if you have a molecule tumbling very rapidly, the correlation time tau c is short. So it is sampling a wide range of frequencies. And if you have a molecule that is tumbling very slowly, that is, it has a long correlation time, then it will only be able to sample a few frequencies because it is tumbling so slowly. So these two functions or equations you can remember. One is the correlation of the spectral density function with the tau c, and another is the correlation function which is related to tau c. So now the spectral density function J, we have already defined that, and we will basically look at two relaxation times, R1 and R2. These are experimentally observed quantities. So from NMR, you can get the value of R1 and R2, which is the relaxation rate constant. So R1 is for spin lattice relaxation or longitudinal relaxation. R2 is for spin-spin relaxation, which is also transverse relaxation. And there is something called a sigma xh, which is the cross relaxation. So suppose you have two spins near each other, then what is the relaxation between those two spins? So these are the three major things. Another is the NOE, which we will look at after some time. So basically, these are experimentally observed quantities. And if you know these quantities, you can predict the spectral density functions. So you don't need to remember these formula. All you need to remember is that, say R1, it is dependent on the spectral density function J at different frequencies. So normally a heteronuclear experiment is done. So you have 15N 1H or 13C 1H. So we will call the heteronucleus as X. So you it different combinations of frequencies are used. So you can have only omega x, so the spectral density function at the frequency of the heteronucleus, then the spectral density function at the sum of frequency of omega h omega x and omega h minus omega x. So basically, these observable NMR quantities, that is the rate of spin lattice relaxation, the rate of spin-spin relaxation, and cross relaxation, these can all be correlated to the spectral density functions. Now, And NOE is basically the cross relaxation. So we looked at cross relaxation sigma XH here, and I said that is the relaxation between two spins. Now, normally, if you have two spins, suppose you have a spin here and you have a spin here, there is a distance r between them. We already know that NOE is directly proportional to 1 by r to the power 6. So the relaxation that is happening between these two spins, which we have called as sigma xh, it is also dependent on the distance between the spins. So there is a correlation between sigma xh and NOE. Just 1 second. Yeah, so there is a correlation between sigma xh and NOE. You can remember this formula. I think this is the only formula you need to remember, that sigma NOE is 1 plus sigma xh by R1, which is the relaxation rate of spin lattice relaxation, into the ratio of the gyromagnetic ratios of H and X, which is the heteronucleus. So NOE can also be, because we know sigma xh can be written in terms of the spectral density function J. We saw here sigma xh can be written like this. So NOE can also be written in terms of the spectral density function. So what we saw is that if we can evaluate the spectral density function at 5 frequencies, one is omega h plus omega x, one is omega h minus omega x, one is only omega x, one is only omega h, and one is 0. So if you can evaluate the J value at these 5 frequencies, you will be able to find R1, R2, sigma h, and if you find sigma h, you can also find NOE. So these are the 5 frequencies that are important: the frequency of hydrogen of the heteronucleus, the sum of hydrogen and heteronucleus, the difference, and 0. The spectral density functions at the 5 frequencies cannot be determined from 3 experimentally determined rate constants by measuring T1, T2, and NOE. So from the experiment, so T1 is basically 1 by R1. T1 is the relaxation time, R1 is the relaxation rate, and T2 is 1 by R2. So from NMR experiments, you can calculate T1, T2, and NOE. But you have 5 unknown things, which are the spectral density functions at 5 frequencies. So somehow some assumptions must be made so that there are only 3 unknown frequencies, so that you can correlate them to the 3 known values, that is T1, T2, and NOE. There are various mathematical models for doing this. We will look at one model which is called the model-free analysis of Lipari and Szabo, which is widely used to obtain information about site-specific internal motions of proteins. So now we will look at the basic experiments for measuring the relaxation parameters. So our main goal is to find the spectral density function. But in order to find the spectral density function, we first need to measure R1, R2, and NOE, or T1, T2, and NOE. So how to do that is we will look at the experiments. This is mainly done by carrying out a series of 2D heteronuclear HSQC or HMQC type experiments. So we will talk about the basic scheme of these experiments. First, there is a preparation time for creating a desirable coherence. Then you have a delay of tau for auto or cross relaxation of the selected coherence. A time period T1 of labeling of the residual coherence by chemical shift of heteronucleus. Then there is basically what this means is that you start from hydrogen, then there is an inept sequence which will transfer the magnetization to the heteronucleus. And then you are allowing the magnetization to evolve in the heteronucleus for this time period T1. This time period T1 is when the magnetization is evolving along the heteronucleus. Then there is a magnetization transferred back to 1H. And there is a 1H acquisition. So you're acquiring the spectra, this FID you are detecting along the 1H channel with broadband decoupling on heteronucleus. So there is 1H15N coupling. We will remove that in order to better resolve the spectra. So these are all pulse sequences in order to do this decoupling. So that ultimately you only record the 1H decoupled spectra uh, along this channel. And then between the first scan and the second scan, there is a certain delay which will allow the magnetization to return back to its initial state that it was at the beginning of this. So the delay has to be sufficient so that you allow the magnetization to return to its initial condition at the beginning of each pulse sequence. So this is the basic layout of a 2D NMR experiment used for measurement of relaxation parameters. Now, the example shown here is basically uh, for longitudinal relaxation, that is for measuring T1. And there are some sequences for suppression of water. We won't go into the details of that. So first, in the relaxation parameters, we will first look at how T1 is measured. So again, that same pulse sequence that we saw in the previous slide is shown here. We'll talk about it in a little bit more detail right now. So initially, there is a 180-degree inversion pulse that inverts the heteronuclear magnetization from SZ to S minus Z. So initially in the 1H sequence, you have an inept pulse sequence which transfers the magnetization to 15N. Now in 15N, if you can see this sequence, one pulse, tau 1, another pulse, tau. This is an inversion sequence. So at the beginning of this sequence, you have SZ in the up direction. At the end of the sequence, it is inverted. It is in the down direction. Then there is a relaxation time period T, during which the magnetization relaxes along the Z-axis. So we are studying T1. So we are studying longitudinal relaxation. So from S plus Z, it is going to minus Z. Slowly, it will recover back to its initial position to become plus Z again. So we are allowing this recovery process to happen, or relaxation process to happen, during this capital T time period. Then there is a 90-degree pulse to create observable transverse magnetization for detection. Now, if you remember in our basic studies of NMR, which we did at the beginning of this course, the detector is in the XY plane. So there needs to be some magnetization along the XY plane, that is your transverse magnetization, so that the detector can detect it and you can get the NMR spectra. So these pulse sequences after the T delay is basically to create this transverse magnetization so that it can be detected. And after that, it is again kind of a reverse. So in inept, there was a transfer from 1H to 15N. Here a reverse inept is done so that from 15N it goes back to 1H and you can detect the FID on the 1H. For T1 measurement, this relaxation block is inserted into the sensitivity enhanced HSQC sequence before the T1 evolution time. So again, we don't need to understand the meaning of each of these words. What you can just remember is that there are certain sequences inserted here which allows this. So basically, we are allowing this longitudinal relaxation to happen. So this is combined with the HSQC experiment. So there is no experiment to only do the longitudinal relaxation. The longitudinal relaxation experiment basically consists of, that is why it is named as 15N T1 HSQC, because you're doing a 1H 15N HSQC, but in between you have inserted a pulse sequence, this T you can see here, which is allowing the longitudinal relaxation to happen. So you're measuring the HSQC, and in between you're also measuring the T1 relaxation time. You can see this, the relaxation process is shown here. So inversion happens here, and the magnetization is in the minus Z direction. As you're allowing the magnetization to relax in a time period T, you can see the magnetization slowly goes from minus direction to 0, and then it regains the original plus Z direction magnetization. So this can be defined by an equation where mz, the magnetization along the Z direction at any time t, is the equilibrium magnetization in Z, that is at the beginning, into 1 minus 2e minus t by t1. T is any time and t1 is your transverse relaxation time. So from the experiment, you will be able to find this t1 value, which is the longitudinal relaxation time. This is defined in terms of product. We don't need to look into this. What you can remember, that there is a factor epsilon, which is the T dependence of the magnetization, that is the signal amplitude. So you can see the amplitude of the magnetization, there is a dependence of magnetization on this capital T, that is the time you are allowing for relaxation. This dependence is represented by epsilon, which is 1 minus 2e minus t by t1. And we know that 1 by t1 can be written as r1. So we can write it as 1 minus 2e minus t r1. This t is the time you are allowing for relaxation. So the epsilon is basically describing the dependence of t on the magnetization. Now there are several, these are just for your information. It's not like questions will come from here. So the experimental setup and data processing includes various things. Some things you can remember, I'll underline here, is that the typical setup for the heteronuclear T1 relaxation measurement includes a recycle delay of 1.5 to 2 seconds. What this means is that you have collected one FID here. So you're again repeating the experiment. So a delay time is given of 1.5 to 2 seconds to allow the magnetization to come back to its initial position. So you can again do the experiment. An array of 8 to 12 T delays ranging from this also 8 to 12 T delays ranging from 5 millisecond to 1.5 second for 15N. So suppose you're doing a 15N 1H HSQC, this T value is varied from 5 millisecond to 1.5 seconds, and you need to do at least 8 to 12 experiments to properly get an idea of the T1 relaxation. So total number of experiments should be 8 to 12, and the T value should vary from 5 millisecond to 1.5 second. So these values you can remember, they can just be asked as MCQ questions in the exam. And there are other things like you can remember that for 15N, you can see these two. So the data acquisition is done with 128 complex T1. So you can see the T1 here. You can change it, so you can get, again, these are not that important, but this is the spectral window width for 1H is kept around 15 ppm, and for 15N it is kept around 35 ppm. So basically what this will do is you will get various, so 2D spectra, you know, on one axis will be the frequency of hydrogen, another axis will be the frequency of nitrogen. So you are carrying out 8 to 12 experiments with the capital T ranging from 5 millisecond to 1.5 seconds. So you will, these are various experimental outputs that you will get. 2D Fourier transform is carried out on all the outputs to get this kind of a different 2D spectrum. Depending on your value of T that you have taken, you will get a different kind of 2D spectra. So you will have a set of 2D spectra. And what you can do is that so I'll just go through it again. Each of the series of spectra is phase corrected after being Fourier transformed. So you will get a series of spectra from the 8 to 12 experiments that you have done with different T. You will get a series of spectra like this after Fourier transformation. Then the phases need to be corrected. So all the spectra are basically of the same phase. And again, these are experimental setups, so they are not important, but this point is important. The amplitude of the cross peak is measured using either the peak volume integral or intensities. So for each spectra, you are calculating the so suppose you're calculating the amplitude of this, So the you choose one particular peak and you calculate how the amplitude is changing with the different. So this is suppose T, T dash, T double dash. So at different values of T, you will get different amplitudes of the signal. And then that can be plotted in a graph. The intensity or volume integral I shown here of the cross peak of residue J is measured for all the spectra at different values of T. You will get a graph. So for this is a residue specific experiment. So suppose you have a protein. Here 3 residues are shown: leucine 24, phenylalanine 36, and lysine 46. For each of these 3 residues, you will get one peak in the 2D spectra. Now, if you measure the amplitude or intensity of this peak, you will get a different value of intensity for a different value of T. And that is what is plotted here. The intensity is changing with T. This is the longitudinal relaxation time, and then you can fit it to this equation. We saw this equation of epsilon, the signal amplitude. So if we fit the values that we obtained to this equation, that is epsilon is 1 minus 2e minus t by t1, or 1 minus 2e minus tr1, then we will fit the values to this equation, and that will help us get the longitudinal relaxation rate R1. So this is the set of experiments for calculating the longitudinal relaxation rate. Now we can calculate R1 for residue specific. We just saw here that we can calculate residue specific. So from each plot, we will get the value of longitudinal relaxation time for that particular residue. So for each, here a protein is shown. You can see it is this protein which is shown. So for each residue of the protein, in the x-axis, you basically have residue number. So for each residue, you are getting a different value of R1, and that is what has been plotted here. What is seen is that for the flexible regions, so for this protein, this is the N terminal and this is the C terminal. So N and C terminal, you can see, are quite flexible. They are not folded in any secondary structures, and they are seen to have high relaxation rate. And for the folded region, this region in the middle, folded region which is folded into alpha helix, beta sheet, and so on, the R1 rates are lower. Now within the folded region also, there are certain regions like suppose this, which is a loop, which is more flexible compared to the folded alpha helix or beta sheet. In those cases, you can see shown in red here, again the R1 is increasing. So whenever you have a flexible region, R1 is high. Whether that flexible region is the N terminal or it is the C terminal or if it is a loop. And whenever you have a well-folded region consisting of alpha helix and beta sheet, the R1s, you can see all these R1s are low. So depending on the value of R1, it will give you an idea about the degree of dynamism in that region of the protein. Now, the lower graph is basically in presence of 8 molar urea. In 8 molar urea, it will completely denature all the secondary structures. And you can see that most of the R1 values are near this line that is shown. You can see if you have a mean line here, in case of the folded protein, there are many R1 which are deviating from this folded line, from this line. But when 8 molar urea is applied, you can see the protein is completely denatured. And so you can see most of the regions have similar values of R1. And that is what happens on denaturation. The secondary structure is completely lost. And this kind of change is seen where suppose you had, if you look at this region, in a folded protein, these regions were so high, it went up to 6. But in a denatured protein, all the R1s become low. They are just around 2.1 or so. Then you can look at this region, the C terminal, where it was around 5. But here again, they have come around 2.1 or so. So most of the R1s reduce to a mean value when 8 molar urea is given to denature the secondary structure. So now we have looked at all about longitudinal relaxation. So now we will look at transverse relaxation or T2. Just give me 2 minutes. Right. So we will look at transverse relaxation. Now, what is transverse relaxation? So initially, again, the magnetization is along the Z direction. Giving a pulse, it is brought down to the XY axis. Now, in the XY axis, due to inhomogeneity of the magnetic field, in addition to spin-spin interaction, what happens is the net magnetization is supposed to be directed along one direction. But that does not happen. It spreads out. You can see there is a spread out. And all the spins start spreading out till eventually you can see the spins average out and the net magnetization becomes 0. After this, what happens? So this is when the pulse is given. Now all these magnetizations will reduce and try to come back along the Z direction, which was the original direction of magnetization. This is called transverse relaxation, where all these XY component magnetizations will reduce. So you can imagine the XY component magnetizations, they are very high. They will all slowly reduce. As the XY component is reducing, the Z component is increasing. Eventually, the XY component will become 0 and the magnetization will fully be restored along the Z direction. So this is your transverse relaxation process. Here the pulse sequence is very similar to that of the T1, but where there was in T1 you had used an inversion scheme. So from Z you had brought to minus Z because T1 was longitudinal relaxation and you wanted to study how minus Z goes back to Z. But here, instead of the inversion scheme, a CPMG sequence is used. So we look into that in the coming slides. In addition, rather than decaying along the longitudinal direction, the heteronuclear magnetization relaxes on the transverse plane during the T period of the T2 pulse sequence. So in longitudinal, the decay was in the Z direction. From minus Z, it was coming back to plus Z. Here the decay is along the transverse direction. Initially, the transverse components completely cancelled each other out. They were maximum. Then the XY components are reducing, Z component is increasing. Finally, the XY components become 0 and the magnetization is back along the Z direction. So what is contributing to this transverse relaxation? One is the spin-spin interaction. Another is the inhomogeneity of the magnetic field. In order to remove this field inhomogeneity, a CPMG spin echo sequence is used. Again, we will look at that as we are coming. And we will, so one is that you can remember the CPMG sequence is used. And another you can remember is basically there is a refocusing that is happening. How does that happen? I'll show you. So imagine the spins are spreading out like this. So it is spreading out in these directions. From here, if you imagine an inversion, so now the spins are like this, but now they will be coming together. So you can see here the movement was in this direction, so they were spreading out. But if you flip them 180-degree along this side, they will be coming together, and then there will be a refocusing of the spins where all these spins will come together to give one transverse relaxation. And then this will be brought back to the z-axis to give you the initial z direction magnetization. So this is the qualitatively what is happening. You don't need to remember all this. So basically it is refocused, and the spins being refocused remain in the identical magnetic field, and then it relaxes back to the z direction. So the pulse sequence is shown here. Again, we don't need to look into the details of that. What you can remember is that the intensity that is, so in the previous case also, we got a plot of intensity with time. Here also, we'll get a plot of intensity with time. In this case, in the previous case, if you remember, the formula was 1 minus 2e minus t by t1. In this case, the formula is intensity I is I0, the initial intensity, e to the power minus t R2. So again, like the previous experiment, you are varying this t with different values of t. Suppose t, t prime, t double prime, you are getting a spectra. 2D Fourier transformed into the normal 2D spectra, we see t, t prime, t double prime. So this t is varied along the x-axis, and in the y-axis you are, so these are again residue specific. So here you can see glutamine, lysine, isoleucine. Suppose this is q, this q53 that you have plotted. You calculate the intensity, plot it along y-axis. So in a residue specific manner, for each residue you will get an exponential plot which you can fit in this equation, which is I is I0, that is the initial intensity. You can think of this point, e to the power minus t R2, where t is this value of the CPMG sequence, how long you are keeping the sequence, and R2 is the transverse relaxation rate, which is what you want to calculate. T can just, 1 second. Now T can be written as 2n, where n is some constant, into 2 epsilon plus pulse width of 180. So we are applying 180-degree pulse in this T. You can see these pulses are 180-degree pulses. You are applying this, whatever is the pulse width that is put here, and epsilon is whatever this time gap is given between these pulses. Time gap is 2 epsilon, you divide by 2 and you get epsilon. So this capital T is calculated like this. So fitting these, so from the experiment you will obtain different intensity at different time. You can fit that plot using this equation, and then you will be able to find the value of R2, that is the transverse relaxation rate. Now again, here there is a certain experimental data setup and processing which you don't need to look into the details of. You need to remember that Similar to T1, here also 8 to 12 experiments need to be done. So these are different experiments, 1, 2, 3. This needs to be done 8 to 12 times with different values of capital T. And the values of capital T can range from 5 millisecond to 150 millisecond. In the previous case, it could range from 5 millisecond to 1.5 second. So for T1, the capital T can vary in a much longer range, 5 millisecond to 1.5 second. But for T2, the capital T should only vary from 5 millisecond to 150 millisecond. And another thing is that the time of the CPMG pulse train is said to be shorter than 150 millisecond. Why? To avoid sample heating problems caused by the pulse train. So we just saw that for T2, the range is very small, only from 5 millisecond to 150 millisecond. And why the range is small is because this pulse sequence that is there, it causes heating of the sample. But we don't want the sample to be destroyed because NMR is a non-invasive technique. So we limit the maximum capital T to 150 milliseconds so that the sample does not heat up too much. Rest is more or less similar to T1. Now, what is, so we can find out in this, so this is a residue specific way. So for this residue, we can find one value of R2. For this residue, we can find another value of R2, R2 prime, so on. So for each residue, we can find a value of R2, and that is what is plotted here. In the previous case, so for the same protein, we had studied the plot of R1, and we saw that for N and C terminal, where the protein is flexible, the R1 value was large, and also for the loop, the R1 value was large. Wherever there is secondary structure, the R1 values was small. The R2 trend is opposite to that of R1. That means for flexible regions, you have small values of R2. You can see that for the N and C terminal, R2 is short. And wherever there is secondary structure formation, R2 values are high. So R2 is the reverse of R1. In presence of 8 molar urea, if you remember, when you put 8 molar urea to R1, what had happened? All the residues more or less had similar values of R1. Same thing happens for R2. When you put 8 molar urea and you completely denature all secondary structure, you can see most of the residues have very similar values of R2. So there is no specific propensity for the secondary structure because 8 molar urea completely denatures the structure. So similar to R1, looking at an R2 graph, you can predict the degree of dynamism in a protein. If the R2 is small, that means the region is very dynamic, that is, it is flexible. And if the R2 is large, that means the region is folded into some kind of secondary structure. So now we will look at how protein folding can be studied using R2. Initially so here we are doing a urea dependent study. Initially you have 8 molar urea and all the residues have similar values of R2. Slowly you are decreasing urea concentration, 8, 7, 5 molar. You can see that as that is happening, secondary structures start forming and the R2 value increases in the middle region, decreases in the lower region. You can see if we look at the 5 molar graph, these values of R2 are going down. These values of R2 are coming up. So some secondary structure is forming in the middle residues. So like that, using different concentrations of urea, you can find that in what residue the folding hotspot is there. That means at what residue the folding is starting to happen. Now, another thing that to remember is that the relaxation rate R2 consists of two factors. One is the intrinsic R2 and one is the R due to exchange phenomena. So that is written as REX. This REX happens in a time scale of millisecond to microsecond. Now, suppose you have plotted R2, that is this net R2 at 0 molar urea, and you get a proper folded protein where the N and C terminal have low R2, meaning they are flexible, and in between there is some folded region, which is why R2 is high. Then you take R2 at a low denaturing condition, very mild denaturing condition, 0.9 molar urea. There are some changes in the R2 value, and you can find out more about the changes if you take delta R2. So you take R2 at 0 molar urea minus R2 at, R2 at 0.9 molar urea minus R2 at 0 molar urea. So these two R2 are subtracted to give you delta R2. Delta R2 is telling about the contribution from this exchange phenomena. So we will come into this more later, but all you can remember for now is that suppose in 0 molar urea there is a certain structure, and in 0.9 molar urea there is some other structure that is forming. The exchange between these two structures can also be found out by this delta R2. That is what is shown in this set of graphs. So here 8 minus 7, 7 minus 5, 5 minus 4, different delta R2s are plotted, and based on the delta R2, we can find out where the exchange is happening. We will look into this more later. So we have looked at R1, the longitudinal relaxation rate, and at R2, the transverse relaxation rate. Now we will look at the heteronuclear NOE measurement. The heteronuclear NOE is determined from the change in intensity of the NMR signal of the heteronucleus X when the equilibrium magnetization of protons in the vicinity is perturbed by saturation in experiments such as transient NOE or steady state NOE. So here what happens, initially a pulse is given only in the proton channel in order to saturate the protons in the vicinity of the heteronucleus. After that, 190-degree pulse is given to the proton. Then it is transferred to the 15N. In the 15N, there is, so the first 90-degree pulse given to the proton, which is this pulse, the first 90-degree pulse given to the proton, combined with the gradient, there is a certain gradient G1, is used to ensure that the 15N magnetization is the only initial magnetization of the experiment. So when the initial 1H 90-degree pulse is combined with this gradient, the entire magnetization is transferred to 15N. After the first 90-degree X pulse, that is this pulse, the chemical shift of the heteronucleus X evolves during T1. You can see this time T1. Here the magnetization is evolving in the heteronucleus channel, that is the 15N channel. And the heteronucleus magnetization is transferred back to the protons after this period is over, that is small t1 period is over, the magnetization is transferred back to proton, and then the decoupling happens and the spectra is recorded in the proton channel. So basically what you need to remember here is that in heteronuclear NOE experiments, compared to T1 and T2, there is an initial saturation phase where the magnetization of the protons in the vicinity of the heteronucleus is saturated. To measure the NOE, two experiments are done. One is with the saturation called NOE, one is without the saturation called no NOE. So you will get a peak intensity ISAT when this saturation pulse sequence is existing, and that is defined as the average that is defined by the average magnetization in the Z direct, the equilibrium or average magnetization in the Z direction of the X nucleus. So this is the X nucleus, the heteronucleus, and the so this is the X nucleus, that is the heteronucleus. Whatever is the Z magnetization in the X nucleus, that is taken, plus sigma xh, which is the rate constant of cross relaxation. We saw the calculation previously, divided by R1 the longitudinal relaxation rate, into the Z magnetization of hydrogen. So this is I saturation, the intensity when the 1H channel is saturated. This can be correlated to the intensity when the 1H channel is unsaturated. That is, the saturation pulse is not there. So I saturation is I unsaturation into 1 plus sigma xh by R1 into the gyromagnetic ratios of H and X. So this formula, you can relate the intensity when this saturation pulse is there and the intensity when the saturation pulse is not there. So this is the formula we saw. The NOE is defined as the ratio of I saturation by unsaturation. So you bring the unsaturation to this side. So the ratio of the intensity of the saturated and unsaturated is 1 plus sigma xh by R1 and the gyromagnetic ratios of H and X. That is the NOE, and the standard deviation of the NOE, known as sigma NOE, can be calculated by this formula, which is the error in measurement of the I saturated divided by the I saturated value squared of both, plus the error in measurement of I unsaturated divided by the intensity of unsaturated squared of both. So this error in measurement of the intensity is calculated from the RMS noise of the background regions. Normally the machine itself does it, so you don't have to worry about that. 15N spins have NOE values ranging from 1 to -4 because 15N, you know, has a negative gyromagnetic ratio. So if gyromagnetic ratio, this is negative and this whole thing is greater than 1, the net NOE becomes negative. So 15N can have negative NOE values, whereas 13C, the gyromagnetic ratio is positive, so the NOE is always positive from 1 to 5. Normally, NOE values of 1 indicate that the protein is very rigid, and NOE values of -4 indicate that the protein is very flexible. We will look at it in this example. So again, the experimental setup you don't need to remember. Just a couple of points that you can remember is that the recycle time of at least 5 seconds is given from the end of detecting one experiment to the beginning of the next experiment. The time delay of around 5 seconds is given to allow the magnetization to come back to its equilibrium position. And rest, you don't need to remember that much. You can just see that. So for the same protein for which we had calculated the R1 and R2, here the NOE is plotted in the Y direction and residue number in the X direction. So you can see that at the terminus of the protein, these N terminal values and the C terminal, the NOE is negative. And we saw that negative NOE means it's a flexible portion. So N terminal is also flexible negative, C terminal is also flexible negative. And from residues around 22 to 94, all the NOEs are very close to 1. NOE close to 1 means that it is a rigid portion of the protein. Indeed, all these residues fall within this folded region of the protein, so it is very rigid. So we will summarize what we have seen. So this is in summary of what we have seen, we can remember that for R1 and R2, R1 is high, R2 is low for the flexible region, R1 is low, R2 is high for the rigid region. And NOE is negative for flexible region, 1H15 and NOE, and positive close to 1 for rigid regions. So all these three parameters, the R1, R2, and NOE, give an idea of the degree of dynamism in the system. Here you have an example of another protein where most of the protein is folded. You can see like this protein had some flexible regions. This protein does not have any such flexible regions. Most of the protein is folded. That is why you can see that NOE is, if you look at NOE, it is all around 0.6. So positive NOE and around 0.6 indicates a rigid molecule. And this is true for most of the residues. So the molecule as a whole is very rigid. Similarly, if you see R1, R1 values are very similar. That means, and also they are you can see R1 around 3 to 4 indicates secondary structure is there. And here all the residues have R1 around 3. So there is a secondary structure in all the residues. R2 also, all the residues have similar R2, meaning they are similarly rigid. But in some places shown by red here, the R2 is anomalously high. If you plot R exchange, you can see that where the R2 is high, there the R exchange is also high. That means the reason for this high R2 is because of exchange phenomena. We saw that R2 is made up of intrinsic R2 as well as the exchange rate. We can find out by plotting the R exchange that since these particular residues, the same residues have high R2 and the same residues have high R exchange. That means the high value of R2 in these places are due to exchange phenomena. Like suppose these two residues, there's a ring here and there is a asparagine here. So suppose there is some exchange between these residues. This will lead to these kind of R exchange values. There is also something called S squared. So instead of the calculating the R exchange, another thing that you can do is take the ratio of R2 by R1. The R2 by R1 plot gives the same information as the R exchange plot. You can see wherever R exchange is high, R2 by R1 is also high. So instead of separately doing another experiment to calculate R exchange, just simply R2 by R1 can be divided to get an idea of the exchanging protons. This sixth graph is a parameter called S squared. We will look at it in the coming slides. So for the relaxation data interpretation, we already talked about the model-free approach of Lipari-Szabo. Now we will look at what are the assumptions in the model. The assumption is that you can separate the internal and globular motions. So a protein can have two types of motions. One is the internal motion consisting of tumbling of the individual residues or loops, and another is the globular motion, which consists of tumbling of the whole protein. The Lipari-Szabo model-free approach assumes that these motions can be treated separately. Now, so this is something we have seen before. We have defined the correlation function before, which was 1/5 exponential of minus t by tau m. And if you do the Fourier transform of the correlation function, you will find the spectral density function, which can again be correlated, which can be related to the correlation time. So these are things we have defined before. Now, using the Lipari-Szabo model, we are first assuming a mostly globular protein. That is a protein like this, where there is no flexible fragment hanging out like the N or C terminal tail. Most of the protein is folded and it's called a globular protein. For such a protein, the overall tumbling can be described by a single correlation time, which is the globular motion, and the internal motions are taking place on a time scale much faster than the overall motion. So the two types of motions, the internal motion and the globular motion, can be separated, and the total correlation function Ct can be written as C0t into Cit, where C0t is defining the globular motion and Cit is defining the internal motion. So this is the Lipari-Szabo assumption that in case of a mostly globular protein, you can separate out the globular motion into C0t and the internal motion as Cit. C0t is what we have already talked about earlier. The correlation function we talked about for a rigid rotor, which can be Fourier transformed into the spectral density function. CIT, that is the internal motion, can be defined by this formula, which is s squared plus 1 minus s squared into exponential of minus t by tau e. Just 1 second. Where s squared is called as the generalized order parameter. For restricted motion, s squared is 1, and for a disordered region, s squared is 0. So if you look back at the previous graph, the s squared is close to 1 for all the amino acid residues, and s squared close to 1 means that the dynamism is completely restricted. That is what happens in this protein. This protein is a fully folded protein. There are no hanging flexible N and C terminals. And so the entire protein is restricted. And so the S square for most of the residues is close to 1. So this is what the S square is, which is called the generalized order parameter. And this is another parameter in addition to the R1, R2, NOE, which tells you about the dynamism of the molecule, more specifically the internal motions. So using this formula, you can find out the correlation function for the internal motion, and you can multiply it with the correlation function of the globular motion, and that will give you the total correlation function. So as we were talking about the Lipari-Szabo model, the assumption is that the molecular overall rotation is isotropic. That means most of the rotation is happening in a, you can imagine the molecule as a as a large globule, and it has an isotropic motion. The motion is not orientation dependent. Secondly is that the intramolecular motions for most of the protein, meaning that the internal motions are much faster than the globular motion, which is something we discussed here as well, that the overall motion and the internal motion is on a much faster time scale of less than 100 picosecond. The internal motion is defined by tau e, because tau e is what we use to define the internal motion correlation function. That is less than 100 picoseconds, so it's very fast. The model-free approach assumes that the intramolecular motions are independent of the molecular overall rotation, which is why we could separate it out into two terms. And conventional model-free protocols implicitly assume that the protein does not aggregate at concentrations typical for NMR relaxation studies. This is also obvious because we did not consider anything for aggregation in this model-free formulas that we have discussed. So you can that is mostly about the model-free assumptions. We don't need to look more into the details of this. Now we will go back to the spectral density mapping. Now suppose, so we were talking about the model-free assumption where the whole rotation is isotropic. That means your protein basically is kind of globular. The protein isn't like has flexible parts and then globular parts. So this is isotropic motion, and this can be used. The model-free approach can be used. But what if there is anisotropy in the motion, which is commonly observed in disordered proteins like this, where you have certain fragments free and certain fragments ordered? Then the analysis becomes more complicated. So here, normally, in this approach, the values of the spectral density functions are sampled at several frequencies. You take the frequency of nitrogen, frequency of hydrogen, sum of frequency of hydrogen and nitrogen, difference of frequency of hydrogen and nitrogen, and zero. So the spectral density is taken at different frequencies. And we already saw before that this is a problem because you need the spectral density function at 5 frequencies, but there are only 3 known experimental observables, the R1, R2, and NOE. So somehow the number of frequencies have to be reduced. So you have 3 known and 3 unknown values. So here an approximation can be taken, which is called reduced spectral density. We know that omega h is around 600 and omega n is around 60. So we will make this assumption that J spectral density function at omega h is approximately the same as spectral density function at the sum of omega h and omega n, because omega h is 600, this is 600, this sum is 660, and this difference is 540. We are going to assume that the spectral density function at the frequency 600 is the same at 660 and 540. So using this approximation, we can ignore the difference and the sum. So instead of 5 frequencies, we will only have 3 frequencies, omega h, omega n, and 0. So now we have 3 unknowns, the 3 spectral density function at 0, at omega h and omega n, and we have 3 observable values, the R1, R2, and NOE. So using the 3 observable values, we can calculate the spectral density function at 0, omega h, and omega n. We have already seen that there are formulas that define R1, R2, and NOE in terms of the spectral density functions at different frequencies. So here an example is given that suppose you have a 500 megahertz magnet. So the 500 megahertz will correspond to the omega h value. Omega n from gyro-magnetic ratio we know is 1/10 of omega h. So omega n will be 50 megahertz. And then you can add 50 and 500 to get 550. You can subtract to get 450, and you can have 0. And then we saw reduced spectral density means we will ignore the sum, we will ignore the difference, and we will only have 3 frequencies, 500, 50, and 0, at which we need to calculate the spectral density functions. So now from the 3 observable values R1, R2, and NOE, we can calculate the spectral density function J0, J omega h, and J omega n. The formula are given here. So these formula you can remember. As I said, you don't need to remember these formulas, but these are the ones which you can remember. So these formula you can remember because these are what you arrive to at the end of everything. So what you can see is J of omega h is 5 by d squared into R NOE, where R NOE depends on the calculated NOE minus 1 multiplied by R1 into the gyromagnetic ratios. So the omega h is largely determined by the heteronuclear NOE. And we know the heteronuclear NOE is sensitive to high frequency motions of the protein backbone. So the J omega h will give you an idea about very fast motions, that is in the picosecond time scale. J omega n, if you look at the formula, it is dominated by R1. So J omega n will give you idea from nanosecond to picosecond time scale. And J omega 0 has equal contribution from, not equal, like similar contribution from R1, R2, and NOE. So J0 will give you information of both the nanosecond time scale as well as slower time scales like microsecond to millisecond time scale. So finding the so from the 3 observable quantities R1, R2, and NOE, we can calculate J omega h, which will tell us about very fast motions in the picosecond time scale. We can calculate J omega n, which will tell us about motions from nanosecond to picosecond time scale, and J0, which will tell us about nanosecond time scale motion, as well as exchange phenomena happening in the micro to millisecond time scales. So from R1, R2, and NOE, we can calculate the spectral density functions. And from the spectral density functions, we will get to know about the different kind of motions happening in the protein that will give us an idea about the protein dynamics. So here you can see for this protein, we have already discussed the R1, R2, and NOE. Now, how does this compare to the plots of J omega H, J omega N, and J0? So you can see that J omega H, it is very high for the flexible region. That is, you can see the N terminal is very high and it is low for the ordered region. So J omega H is large. Yeah. So J omega H is reporting mostly about, we saw J omega H will report about very fast motion in the picosecond time scale. So J omega H is reporting about the picosecond timescale motion of the N-terminal tail. And J omega H we can see is very high for the flexible regions and is very low for the ordered regions. J omega N, the plot is very similar to R1. If you compare the plots of J omega N and R1, they are very similar. In both, the initial values are high and the ordered region values are low. And J0, it is dependent on all three, R1, R2, and R3. So, and within R2 also, if you want to find, we know R2 consists of the intrinsic R2 as well as the exchange R2. So the J0 can even give you information about the exchange phenomena. So basically, from R1, R2, and NOE, you can calculate the J omega H, J omega N, and J0. And these will also give you information about the dynamics of the molecule in different time scale. Omega H will give you idea about the picosecond motions. Omega N will give you idea about nanosecond to picosecond motion. And J0 will give you idea about some of the fast motions in nanosecond and rest slow motions from microsecond to millisecond, which include the exchange phenomena. Finally, you can define a linear relationship. So suppose you have J omega N or you have J omega H, they can be correlated to J0. So J omega N or J omega H is alpha times J0 plus beta. Now, so you can plot J omega N or J omega H in the y-axis, and you can plot J0 in the x-axis. You can see there are two kinds of values. In the low, so let us look at the first plot, which is J0 versus J omega N. In this first plot, at low J0 values, this is the low J0 value range. There is one kind of linear fitting graph. So from the linear fitting graph, from the slope will give you alpha, the intercept will give you beta. You can see the values of alpha and beta. And then there is this, once the value of alpha and beta is found, you can put it in this equation given here, where omega is the Larmor frequency of 15N or 1H. Using this, you can find out the correlation time tau. So from the plot, the slope will give you alpha, intercept will give you beta. You put it in this equation and find the value of tau. The value of tau is different at low J0 values, and at high J0 values shown by these black circles, the linear fitting is again different. So you will get a different, so suppose for this you get alpha 1, beta 1. For this you will get another set of values, alpha 2 and beta 2. So that will give you, this is another set of values, alpha 2, beta 2. And that will give you another correlation time for high J0 values. Similarly, if you plot J omega H versus 0, for low J0 values, you will get 1 alpha, beta, and 1 tau. And for high J0 values, you will get another alpha, beta, and another tau. So you can also find out the correlation time. So I'll repeat again. From NMR, you can find out R1, R2, and NOE. Using R1, R2, and NOE, you can calculate J omega H, J omega N, and J0 using these formula. And from the three J spectral functions, you can find out alpha and beta. And from alpha and beta, you can find out tau, that is the correlation time. So all kinds of parameters can be found to define the dynamism of the protein. You can see that you are getting different correlation times. At low J0 values, you are getting idea about motions in the nanosecond time scale, in the microsecond time scale. At high J0 values, you are getting nanosecond time scale, and so on. Even you are at high J0 values versus omega h, you are getting idea about a motion in the picosecond time scale. So in all kinds of time scales, there are different motions, and you are getting an idea about all these motions through these three experiments: the longitudinal relaxation rate R1, the transverse relaxation rate R2, and the heteronuclear NOE. I think that covers all the lectures of week 11. As always, we don't need to go too much into the mathematics of it. You just need to remember the basics. So now I'll go into the assignment questions of week 10. One question is, which one of the following statements is true for in vivo NMR? So let us look at in vivo NMR. What are the advantages and disadvantages? Advantages, we know that we are directly measuring the drug levels in the target organ. Then it can be repetitively used in the same patient, and it's a very non-invasive technique. Second, the drawbacks on the other hand is that the sensitivity is very low. So this option 1 that is there, that high resolution data can be obtained, is wrong, because sensitivity is low, the resolution will also be low. Then only molecules with unrestricted mobility are visible. Then you have that prolonged data acquisition may be required. You know that in vivo NMR, like the MRI we do, we might need to keep the patient inside the MRI machine for up to 1 hour. So a long data acquisition time is required. This is because we cannot give a strong magnetic force field that will affect the patient. Because we are using a low magnetic force field, the data acquisition time also has to be increased. Then we have that the observed signals may have various anatomical origins. That means, suppose we are looking at 1H NMR. The 1H NMR can be part of the drug, but it can also be part of, say, your blood. Blood has 70% water. So the 1H NMR signal can come from the blood. It can come from any of the protein, lipid, carbohydrate, any organic molecule in the body. So signals originate only from labeled probes is wrong. It can also originate from anything inside your body. And we have already seen sensitivity is low, so resolution is poor. So in vivo NMR is highly sensitive is wrong, because sensitivity is low. So what is correct is that data acquisition is extensive. That is correct, because we have already said that we can use the in vivo NMR repetitively on the same patient for a long time in order to have extensive data acquisition. So the correct answer is option D. Then you have a question, why is 19-fluorine a good probe for in vivo NMR? Let us look at the advantages of 19F. Firstly, is that the fluorine atom remains intact during biotransformation. Here an example is seen. This FU, fluorine containing drug, is given. It is breaking down into various metabolites, metabolite 1, which is an aldehyde, metabolite 2, which is an acetyl. And all these metabolites have the fluorine atom, because the fluorine atom remains intact in all the metabolites. That is, the fluorine atom remains untransformed post-metabolism. This is true. Then we know that fluorine spectra has a large spectral width. You can see the spectral width here, it ranges so high. So because of the large spectral width, the signals can be resolved. So this is also correct. Then fluorine has high natural abundance. We know the abundance of fluorine is 100%. It does not have any other isotope. So this is also correct. So the correct answer is all of the above, or D. Then you have a question. Looking into the limitations of spectra obtained from in vivo conditions, which probe is generally used? Let us look at the different limitations. For 1H, the limitation is that the proton chemical shift range is small, only from 0 to 15 ppm. And we know that there is a lot of coupling in proton NMR, which leads to a lot of multiplicity. So for one peak, you can have a quartet. For another peak, you can have a triplet. So when there are many protons, resolving this becomes very difficult. And another very big disadvantage is that inside the body, you have a lot of water, protein, lipid, and all of these will also give proton signals, which will interfere with the proton signals of the drug. So this is not a good probe. 14C is not even NMR active. 13C is NMR active, but the option is saying 14C. So this cannot be used because it is not active by NMR. Uranium-235 is radioactive. It is harmful to the body. So considering this, 31P is the correct answer. And one advantage of 31P is that it has 100% natural abundance. That is, it has no other isotope. So it's a very sensitive nucleus. So the correct answer is D, that is 31P. Then you have a question asking that for samples for assessment of NMR specific drug metabolism, which of the following can be used? We know that normally for the key diagnostic fluids, either plasma, serum, urine, or saliva is used. And for other specialized locations, you can use things like cerebrospinal fluid, pancreatic fluid, and so on. But sweat is not applicable because in sweat, it is just a release of water and some salts from the body. You cannot detect any of the drug metabolites in sweat. Same for hair. Hair is just made up of keratin. The drugs are in your bloodstream that is carried out through your urine. So the correct answer is urine, that is B. Then the question is asking that which one of the following options indicate NMR isotopes having a spin value of half? So if you look at the table, you can see 1H has a spin value of half. 15N also has a spin value of half, but 10 boron has a spin value of 3. So this is crossed out. Then 31P has a spin value of half, but 7 lithium has a spin value of 3 by 2. So this option is also cancelled out. Here again 10B, 7 lithium, these are not half, this is cancelled out. So the correct answer is 3, which is 1H, 15N, and 31P. So what you can do is you can remember this spin column, which will help you remember that which NMR active nuclei had what spin, so that at least if you can't remember all, at least remember which has the spin of half. So 13C also has half, 19F, 195 platinum. At least you remember which nuclei has the spin of half, because that is the most important spin active nuclei that we use. So the correct answer is D. Then you have a question. Which of the following is false when considering limitations associated with using 1H as a suitable NMR probe for drug metabolism analysis? We have already seen that 1H has a low chemical shift range. So this is true, but it is asking which is false. So this is out. Then peak overlap due to resonance from body fluids. Again, this is a real drawback. It is not false. So this is out. Decreased JJ coupling is wrong. So it is false and it is the correct answer. 1H has a lot of JJ coupling. We just discussed. In 1H, you can have quartets, you can have many other couplings, and they will all overlap with each other. So there is an increased JJ coupling. That means JJ coupling decreased is false. And the question is asking which is false. So the correct answer is C. Then you have a question. Drug designed to enhance bioavailability of the drug includes which of the following steps? So, does it include modification of a utilized NMR probe? That is wrong, because NMR probe is just used to detect how the drug is getting metabolized in the body. NMR probe can't be used to design a drug. You can use an NMR probe to find out about the receptor binding site and the target binding site, but varying the NMR probe will not help in enhancing the drug. So that is wrong. Or repurposing the drug for a different target, that is also wrong, because you have a fixed target. You can change the drug structure to better suit the target, but we don't change the target itself. So C is also wrong. The correct answer is B. That is, you change the structure of the drug. You can change different functional groups in the drug in order to make it a better drug, enhance its bioavailability, and so on. So the correct answer is B. Then you have a question. Which of the following NMR assisted drug discovery methods requires labeling of the target biomolecule? So if you remember the technique of NMR solve, which we discussed in the previous class, basically what happens when we say protein family, it means all the proteins which have one binding site that is conserved in all members of that protein family, and the second binding site can vary. So what is done in such a protein family, which have the first binding site is same in all the members of the protein family, the protein is labeled selectively. The residues around that binding site are labeled so that we can find out which are the residues that are interacting with the drug. And between the first and second binding site also, there are some probes given in order to find out that what is the orientation between two binding sites. So what this will do is that the first set of probes shown by gray here will tell us which are the residues of the protein that are interacting with the drug. That will help us increase the binding of the drug molecule, change the functional groups as in such a way that the binding is higher. And the second kind of probe shown by red here, what that will do, it will tell us that how to design the linker. So the orientation of the common ligand mimic in the binding site is determined to provide a basis for the design of a linker which is directed into the specificity site. The second site is called the specificity site because it is different in each member of the protein family. The second probe, this red color here, is telling us about what are the orientation of the residues between the two binding sites so that we can design a linker of appropriate size in order to connect with the second. Suppose we have a second fragment here, which is fitting into the second binding site. So how this linker will be designed, that information will be given by this probe. So in this technique, we are labeling the protein, which is the target biomolecule. And the label of the protein is telling us what are the residues of the protein that are interacting, which will help us design the drug for the first binding site, and what are the residue between the two binding sites so that we can design the linker to connect the second fragment of the drug. So the correct answer is B, that is NMR solve. Another question is there. Ligand mediated chemical shift is the mainstay for which of the following experiments? We already saw that NMR solve, it uses ligand mediated chemical shifts. That means to find out that which ligand is binding the best. So uh, basically you do 2D NMR and you see the shifts in the HSQC spectra. If you remember, if the ligand is binding, suppose this is your 2D, you will have shifts like this. So with increase in the ligand concentration, the chemical shifts will be there. So depending on that, you can find out, design the best ligand for position 1 and position 2. So NMR solve does depend on the ligand mediated chemical shift. Let us look at the other two methods. In case of SAR, again, ligand mediated chemical shifts are important because you have to screen a large number of ligands and find out which is the best binding for position 1. Similarly, screen a large number of ligands and find out the best binding for position 2. And then you can link the two ligands with an appropriate linker, and the net resultant drug based on the two fragments will have a much, much higher binding than either of the two fragments by themselves. So here also, in order to screen the ligands, this kind of chemical shift is done, where you are seeing that this kind of shift will indicate strong binding. So SAR by NMR is also involved ligand mediated chemical shift. And ILOE means intraligand NOE. Basically, once you optimize the two fragments for the two binding sites, you can calculate NOE between the hydrogens of the two fragments. And whichever hydrogens show NOE, or rather ILOE, that means those hydrogens are close to each other. So if you can build a ligand so that those hydrogens are build a linker so that those two hydrogens are close to each other, that will be an appropriate linker for a high binding drug. So again, to find out which hydrogens are interacting, we find out the ligand mediated chemical shift of the two ligands in the two fragments in the two binding sites. So this also involves ligand mediated chemical shift. So the correct answer is D, that is all of the above. And for the final question of assignment 10, the question is asking which of the following statement is correct for NMR based analysis of a potent and successful ligand molecule. We know that, let us look at each statement. First statement is saying no chemical shift observed on increasing ligand concentration. That is wrong. We just saw that for a ligand to be successfully binding, there has to be a chemical shift change in the 2D or 1D spectra. 2D spectra can shift like this. 1D spectra, suppose initial was here, final can shift somewhere here. So there has to be a chemical shift change. So no chemical shift change is wrong. Peak intensity remains unchanged. This is also wrong. We know that intensity does change. It can increase or decrease depending on binding. So this is wrong. Cannot be resolved due to fast exchange between target and ligand. But if you cannot resolve it, how will you know if it is binding or not? So that is also not good for a successful ligand molecule. What is successful is line broadening is happening. Why does this line broadening happen? Ligand is a small molecule, so the relaxation is slow. That will give you sharp lines for the ligand. While the ligand protein complex is a large molecule, so the relaxation is fast, and the ligand protein complex will have broad lines. So when the line width undergoes sufficient broadening, that means the ligand is no longer free, but the ligand protein complex has formed. So if this is observed, that means it's a successful and potent ligand molecule. So the correct answer is C. That covers all the slides of this class, and I'll end the class here. As always, both this and the slides will be uploaded. We will have one more class and then a revision class to go through all the whatever we have learned in all the 12 classes. So that will be all for today. I'll stop now.